Welcome back. Today we're continuing our discussion of light, and in particular, we want to get into the wave-particle duality. And
Is it a particle? Is it a wave? Is it both? What is a wave? What is a particle?
what happened? Why did people get so confused about this? Why did they eventually agree, particularly at the Solvay conference in the 1920s, I believe it was, to ratify the fact that light was just a duality? It was something impossible, but forget about it. We're just going to move on. So we're talking a bit about diffraction last time, and we walked through a material explanation using our radioelastic model of the atom for how it is that light can appear to interfere with itself and what's going on there. But an interesting question comes up when you start doing this experiment with what's called single photons. Theoretically, if you lower the power of the emitter, you can get down to a place where, by calculations, you're only emitting one photon at a time, and you still get these interference patterns. Now, there's a couple of possibilities for what could be going on here. Of course, under our conception of the atom, we have these thinned filaments which are essentially responsible for deforming and conducting the power of light. And so, on one hand, it's conceivable that because light is traveling in individual structures, that the discrete quantized steps of that light could be thought of as individual filaments being deformed. But another possibility came up when we met with Eric Reiter, who's a garage experimentalist, and his model for light comes down to thresholds. And can you maybe reorient us towards the idea of thresholds at the detector, and maybe the idea that there's something else going on here?
Well, basically, Eric Reiter's unquantum effect is saying that you don't know the starting condition of the atom at the detector. And so if you shoot a photon at an atom that is at a higher energy state than you think it is, like it's more than halfway to the state where it emits or does the behavior that you're trying to detect, that when you send an impulse to it, there is a level at which it will react that is unknowable. Do you think that that's a decent?
It's like, essentially the idea, I think, is something like the atoms require a certain amount of pressure to go into them, photonic pressure along these filaments, before they'll kick over into a new shape, which will result in the emission of a photon or a chemical change that is seen at the detector, let's say an electron event, which is captured by the photodetector. And sometimes these individual filamentary deformations, what we might call, well, sometimes these are not enough pressure to kick the atom into a new shape. Sometimes you have to, sometimes it's halfway there. It's got a lot of tension in it already.
And so is that what you're saying is happening at the dark spots then?
That's what I'm saying is what's happening in terms of individual spots kicking off. In reality, the dark spots and light spots are happening all the time. The reason that you can see them sequentially, where you can fire the photons one after another, is because you're building up towards this threshold where the event will pop off and kick the detector over.
Oh, that's interesting. But so, okay, so the idea is that when the filament. Okay, so this is actually really confusing to me because if you are sending one photon at a time, are you sending one filament's worth of signal?
You know, that's what I probably would have said to you like a year ago, is kind of the way I was thinking about it. But after thinking about this a little more intensely, it makes more sense to me that since there's multiple filaments stemming from an atom, and all those filaments must be feeling the pressure of the surface.
Yeah, like it can't possibly just send out like one filament's worth of material.
Right. So when we started talking with Eric, it really got me thinking about the fact that these particles, which are measured, are actually just detection events. And the detector has a threshold. So even though the wave pressure is coming and interfering at all times, anyways, in the background, each one of those little detector events is going to kick off sequentially as the pressure builds to the threshold level.
So basically the idea is this: when you lower the output energy of your emitter to the degree that you are measuring the output of a single photon, in a filamentary model, there's no way for you to put out a single photon. And so what's really happening is that you have, let's say, X number of filaments that are able to interact through the slit, and they're behaving the same way that they would behave if you had more photons, if you had more photonic energy there. But in reality, you just have across the slit just enough energy to say that you have one photon, but that's distributed amongst all of the filaments that are going through the slit. And so they're interacting the exact same way that they would be interacting before with the push-pull, but the atoms that are on the detector where you see the final summation of the impacts require more time for them to be able to charge up enough along this threshold model to be able to actually click over to say that there was an impact here. Is that what you're...
That's absolutely right. And I think that's where we're at with explaining the wave-particle duality. In reality, we're talking about waves of deformation radially extending in every direction, essentially. Sure, they can be collimated and reflected and directed and all this stuff, but they're happening, the phenomena is fundamentally wave-based. However, the detections, and this really wraps into the idea of what is a particle in mathematical physics, because when you push on the concept of particle hard enough, you realize that they're talking about a detection event, or a theorized detection event, right? The collapse of a wave function, or something like this. And so in each one of these cases, you're actually talking about some event that's an interaction.
Because you never can build... I mean, maybe like an atomic force microscope could build a detector that was one atom big. Because I think that the tip of the AFM is
you can do one atom, but you're not going to be able to like do one, like what are these different measurements? Like what is a particle? When you talk about a particle like an electron or something like that, which is considered a particle in mathematical physics, it's the collapse of a wave function. It's a momentary exertion of that whole phenomena all at once.
Yeah. And so a lot of the way that we interpret quantum mechanics has to do with the detectors and what the detectors are doing, which is why when we talk to Eric Ryder on the podcast and when we talk to Carver Mead, we spend so much time asking those questions. Like, what is being measured? How is it being measured? What are the things that are happening on the atomic level in both emitter and detector and on the flight path in between? Because only when you really start to understand that there is not a magical, appearance at the emitter and then the appearance at the detector and nothing in between them, like only if you really start thinking about that flight time can you start to understand some of these weirdnesses. And so I really like fitting the threshold model in with this. It's really...
I think it kind of bails out the quantum mechanicists also, because their standard idea is that the photon goes through both slits at once anyways, but they sound a little crazy because they claim that it's a particle also. And so, if you realize the particle is just the detection event, then everything starts to smooth over and it makes a lot more sense.
And the goal is to not kick the machine. The goal is to be able to improve the models, to move them further. In no way, shape, or form is any part of this project talking about that quantum mechanics is wrong and all these people are stupid and they don't know what they're talking about. It's just the fact that all models are incomplete. And if you can push the edge of what is completeness, then you can actually understand what's happening, and that's what's exciting.
Yeah, we're really just talking about a minor chiropractic adjustment here. So yeah, it's not magic, it's material in motion, just like everything else here at the Material World. And we'll see you guys next time.